So we've defined the Ito integral as a map that sends a process, f in h2, to another process, which is the process that sends t to the integral from 0 to 1 of the indicator function of 0t of s, f of s dbs, and we've seen that we need to interpret this process here as the unique continuous martingale that matches this process to random variable Ito integral here almost surely. And there's a unique continuous martingale that does that, right? So this is our extended Ito integral as a map that sends a process to a process. Now, this is almost good enough for all our purposes in this course, except for the fact that our Ito integral is at the moment not good enough to take the process f to be any continuous function of the Brownian, right? The problem is that I'm asking for the process to be in H2, and H2 is maybe just a little too small to be completely useful, right? For instance, if you take f of t equal the exponential of bt to the 4 for all t in 0, 1, is that in H2? Well, let's compute the expectation of the integral from 0 to 1 of f of s squared ds. What is that? This is the expectation of the integral from 0 to 1 of this expectation, and so let's compute directly the expectation. This is 1 upon square root of 2 pi s times the integral over r of exponential x to the 4, 2x to the 4 times exponential minus x squared divided by 2s dx ds, right? That's the because the Brownian is Gaussian distributed. So this would be the formula for computing this L2 norm of the process f, and of course this gives me plus infinity because this integral is not convergent, right? The exponential minus x squared is not decaying fast enough to compensate for the growth of the exponential 2x to the 4. So although this is a very nice continuous function of the Brownian, it cannot be Ito integrated with our theory at the moment because it's not in H2. So we're going to extend the Ito integration from H2 to a larger class called L2 log in order to remedy that problem and be able to Ito integrate such an object. Now, in order to do that, we're going to use stopping time. So we have to make a little break in the course of our development of the integration theory and have a closer look at the property of our Ito integral and how it reacts to using a stopping time. So the question we need to answer now is a question of uniqueness. We need to understand what happens if we stop the process f at a stopping time, right? If I have t as stopping time, that's always with respect to the Brownian filtration, and I'm integrating from 0 to 1, the process stopped at the stopping time tau. Right. So if I stop the process, is that going to mean that I'm just stopping the corresponding integral? So what I want to know is, I want to know if I have two processes that agree up to a stopping time. So if I have this process and I stop it, and it agrees when I stop it with another process, let's say they're both in H2 such that everything makes sense, and that's for all s in 0, 1, does that imply that the corresponding Ito integral of f, if I stop it at the same stopping time, is equal to the Ito integral of g stopped at the same thing? So put in another way, I have two processes, they agree up to a stopping time, and I'm asking whether or not the integral will also have to agree up to a stopping time. It seems obvious that it should. Unfortunately, I cannot take such an indicator function in and out of the integral because tau depends on omega and my integral depends on omega. So I cannot just use linearity of the integral and just pull out such an indicator function. So this is a little technical difficulty that we need to address, and we need to show that our Ito integral is satisfying such a uniqueness property. So stopping a process, if two processes agree up to a stopping time, then their Ito integral have to agree up to a stopping time. So let's see the theorem and let's see its proof. So here is the statement of the theorem in its simplest form. So in the simplest form, I'm going to take my process to be in H2, but also in L infinity. We'll remove the extra L infinity assumption in a corollary later. We have a stopping time with respect to the Brownian filtration. And what we're going to do is we're going to suppose that our process is 0 up to that stopping time, right? So I would like to show that if two processes are equal up to a stopping time, the Ito integrals are equal up to that stopping time. So I subtract these two processes that have to be equal, and I get a new process that has to be 0 up to that stopping time. And what I want to show is that the difference of the integrals the integrals of the two processes that are equal up to a stopping time are the same up to a stopping time. Therefore, the integral of their difference has to be 0 up to a stopping time. So this theorem 4.13 is what we need to prove now. Okay, so let's prove theorem 4.13. So in the first step, we're going to look at the case where f is in H2 not. And at the end of the day, any f in H2 can be approximated by f in H2 not. That's the way we define the Ito integral. So this is what we need to understand first. So I look at an f that is of the form f of s omega equal a finite sum of aj's of omega times an indicator function of a time interval tj to tj plus 1, and I look at that at s, and that's defined for almost every s in 0, 1 and almost every omega in omega. And the time interval, okay, form a partition of 0, 1, and the AJs are all FTJ measurable, and they're in L2. Right. Now I'm assuming that this is 0 up to the stopping time nu. So I'm assuming this. I'm assuming this for almost every s in 0, 1 and almost every omega. But I could also redefine my process on that set of measure 0 where this doesn't hold to be 0. So I can, without loss of generality, assume that this is for every s in 0, 1 and for every omega in omega. Now, what does that mean for the coefficients aj of my process f in H2 naught of omega, that I have this property, right? So let's take an omega in omega and a j between 0 and n minus 1 and assume that tj is smaller than nu of omega. So if tj is smaller than nu of omega, then what I have is that if I take an s, I can find an s in 0, 1 such that tj is below s and s is below n of omega, nu of omega, right? Now, for such an s, fs of omega is equal to aj of omega, and s is smaller than nu of omega. Right? So aj of omega has to be 0 by just picking such an s whenever tj is smaller than nu of omega. So we've proven that for every j, aj, if you stop it, well, if you consider it when tj is below nu of omega, has to be 0. Okay, now what does that tell me about the integral of that process? Well, when I integrate the process, fs dbs, then what do I get? So let's say that t is between tm and tm plus 1 for some m between 0 and n minus 1. Right, then this is going to be the sum up to m minus 1 of the aj btj plus 1 minus btj plus am bt minus btm, right? That's the definition of the Ito integral for an H2 naught process. Okay, but what can I say about, so this is, let's say, evaluated at some omega. And now what can I say about the coefficients in here? Well, if t happens to be below nu of omega, t is between tm and tm plus 1, and nu of omega is above t. So nu of omega is then above all of the tj up to tm, right? So the product j equals 0 to m of the indicator function of 0 nu omega tj. Right. T is above nu of omega is above t, so in particular it's above tm, and in particular it's above tj for all the tj's below m. So this is equal to that. And now what have I got? I've got that this has to be equal to, because nu of omega is above all of those tj's. So this is a sum j equals 0 to m minus 1 of aj of omega whenever tj is below nu of omega, and then the same thing on that last term, it's am of omega with nu of omega above tm times bt of omega minus btm of omega. Okay, but this is 0 and this is 0, so the entire thing is 0. So for an H2 naught process, you can read directly the fact that it satisfies the assumption of the theorem. Now, what do I need to do to go to the full theorem from this first case? I need to approximate my process, my H2 naught process, my H2 process by a family of H2 naught processes. So I'm going to take f in H2, and we'll see that it's helpful to also assume it's in infinity. And then I'm going to pick a sequence fn of elements in H2 naught, and then what I want is that fn minus f in L2 norm, that's L2 of omega cross 0, 1, goes to 0 as n goes to infinity. So it is a approximating sequence in H2 naught. So I need to give a an expression for that. So I'm going to write fn of omega s as the sum j equals 0 to, okay, I'm going to pick my approximating sequence just to simplify matter a little bit, such that this is going to 2n minus 1 and my a j n of omegas are here, and I take my time intervals of the form j divided by 2 to the n and j plus 1 divided by 2 to the n, which I can always do, right? It's one of the possible construction. You can refine your partitions such that it's over this time interval, just to simplify notations a little bit. Okay, now I'm going to look at a modification of that approximation sequence. That's going to be better for my purpose. So I'm going to define fn tilde of omega s. This was defined for every omega and for every s. And now I'm defining a approximation where what I do is stop this appropriately. So I'm going to stop things, right? So my nu of omega is below that j of 2 to the n, and I want my s still between j2 to the n and j plus 1 2 to the n. Now the point of defining this fn tilde of omega as opposed to just using fn is the following, right? What happens if I stop my process at nu of omega, right? I force s to be to be below nu of omega. So if I look at that, okay, this is going to be 0 for all omega in omega and for all s in 0, 1, because s being below nu of omega implies that nu of omega, and and if s is in an interval j over 2n, j plus 1 over 2n, then of course nu of omega would have to be greater than j over 2n, and that would contradict the fact that I'm forcing nu of omega to be below j over 2n. So my fn tilde is a process to which a family of H2 naught process to which I can apply the first step, as in they satisfy the assumption of the first step. And what I need to show is that this modification of fn actually also approximate f. So we need to show that fn tilde minus fn in L2 norm goes to 0. And then I would have a approximation of my process f by a sequence of processes in H2 naught that do satisfy, let's put a nice box around that do satisfy the assumption of step 1. Okay, so let's prove this convergence, that fn tilde and fn have the same limit, namely f. Now remember, talking about this limit f, that f of omega and s is 0 up to the stopping time, right? So if my s is before the stopping time, then I get 0. So because of that, right, I can replace fn by fn times the indicator function of the complement of that set. So 0 s nu of omega, and then this process will also converge to f in L2 norm, because f or f times this indicator function is the same thing as n goes to infinity, right? The difference when you're not on that set is 0 because of the assumption on f. So what we need to show really is that fn tilde minus this process, so minus the process that sends omega s to fn omega s indicator of 0s nu of omega, we need to show that the L2 norm of that goes to 0 as n goes to infinity, and that would ensure that fn tilde goes to f. Okay, so let's prove that. Now the point is, these two things cancel whenever your nu of omega is below a j over 2n, and your s is between j over 2n and j plus 1 over 2n. So when you look at this cancellation, what you find is that this quantity here that we need to show goes to 0 is equal to the integral from 0 to 1, the expectation of the sum. Actually, let's write that explicitly. J equals 0 to 2n minus 1 ajn of omega, and then you're left with the things that haven't been cancelled. That is to say, when nu of omega is above j over 2n. So let's write it like that. Nu is above j over 2n. That's an indicator function in omega. And then I have the indicator function, of course, of s being between j over 2n and j plus 1 over 2n. Then I square that, and then that's dp omega, and then that's ds. Now, there's only one element of that sum in J that is non-zero for any given S. So really, this integral of a sum squared is really just a sum outside of the integral squared by orthogonality. So you get that. Ajn of omega squared, and then the indicator function when nu is greater than j over 2n, right? Because the part where nu was smaller than j over 2n was cancelled by fn tilde. Can do that. Maybe lose an endpoint that doesn't change anything to the integrals. Now I'm using my assumption. So using the assumption, I have that this quantity here is going to have to be smaller than the subnorm of f squared. Right? Why is that? Because the definition of the AJN when you write up your approximation is an average of the values of f, and an average is always smaller than a maximum. So you can control the AJN for every j and every n by the subnorm of f, by the way they are constructed. And then you get this sum. Now you're integrating between j over 2n and j plus 1 over 2n. And what are you taking the integral of? Now that I've got rid of the ajn, just controlling them, not particularly smartly by their supremum, I'm left with the probability that nu is where is above j over 2n, and I should have said from the start it also has to be below s, right? Because if not, the whole thing is 0. So both the fn tilde term and these terms will be 0 if nu of omega were not below s. And if nu were to be not above j upon 2n, below j upon 2n, then this will cancel with that. That's the idea. So what I'm left with is the probability that nu is between j over 2n and s. And then I have that ds. And now controlling this is relatively easy because so this is certainly controlled by the sum j equals 0 to 2n minus 1 integral j upon 2n to j plus 1 upon 2n times the probability of nu being between j upon 2n and j plus 1 upon 2n, right? ds. Okay, so no, this probability doesn't involve s anymore, so I can integrate in s, and I get subnorm of f squared. Integrating in s gives me a 2 to the minus n, and then I get the sum j equals 0 to 2n minus 1 of the probability that nu is between j upon 2n and j plus 1 upon 2n, and then this sets at disjoint. And you can, so the sum of their probability is the probability of the union, so this entire thing is smaller than the subnorm of f squared divided by 2 to the n times the probability that nu is smaller than 1. Whatever that probability is, it is smaller than 1, so this itself, so this is smaller than the subnorm divided by 2 to the n, which certainly goes to 0, as n goes to infinity. So what have we shown? We've just shown that fn tilde tends to f in L2 norm. So we've shown that fn tilde minus f in L2 norm tends to 0. That means fn tilde is an approximation of f using H2 naught processes that satisfy the assumptions of step 1. Now by step 1, what can I say about the integral of fn tilde, right? The integral from 0 to t of fn tilde dbs. If I look at that whenever, up to the stopping time, so whenever my t is below the stopping time nu of omega, right, and I look at that, then this has to be 0 for every n in n by step 1. Okay, but what is the Ito integral of f? It is the limit in L2 of the Ito integral of the fn tilde. So if I take a subsequence that converges almost surely, so well, let's write that first. The integral from 0 to t of s of f, not f tilde, f of s dbs, right, is equal to the limit in L2 of this integral. That's by definition of the Ito integral, because fn tilde is a approximating sequence. So this goes to 0. So taking a subsequence, that's an appropriate subsequence, we can have that the integral from 0 to 1 of integral from indicator function of 0 t of s, f of s, dbs of omega is the limit of the integrals fn tilde s dbs of omega for almost every omega. Almost surely, right? We take an almost sure limit of a subsequence of the sequence that converges in L2, right? By the fact that you can always do that when you have convergence in L2, there is a subsequence that converge almost surely. And now taking that subsequence, right, what do we have when we apply step 1? We have that up to the stopping time, this thing that we're taking the limit of is always 0. Okay, so what does that exactly say, right? It says that for every t in 0, 1, there exists a set that depends on t in sigma that has probability 0, such that for every omega not in that set, whenever I am below the stopping time, my integral is 0. That's just a limit. It's an almost everywhere limit, so it's a limit for all omega not in that set of probability 0 of something that is equal to 0. That is almost my conclusion, but not quite, right? Because I want to be able to say that there exists a set of probability 0 outside of which this holds for every t. So I really want to exchange this quantifier, right? I don't want for every t to find a set AT. I want to find a set A that works for every t. Now, I want to take the union of all these ATs, but if I do that over all of 0, 1, it's a non-countable union, I'm not sure I get something of probability 0. But I can do that if I work on all of the rational time only. So there exists an A, that's really the union of AT over all t rational, that has probability 0, such that for every omega not in A, and for every t in 0, 1 intersected Q, I have that the integral, that whenever t is below the stopping time, then the integral is 0. The integral up to t of f of s dbs. Now, how do I go from that to the full result? I use continuity of the process. So remembering that t goes to this integral is continuous, okay, almost surely. So up to throwing away another set of measure 0, there has to exist a tilde in sigma that has probability 0. Right, that's going to be the union of A and the set on which this is discontinuous, such that for every omega not in that set, A tilde, and for every t, this time in 0, 1, I take the limit of things equal to 0, and I still have something equal to 0. So for these omegas and t's, or more precisely for all t, but for those omega such that t is below nu of omega, so maybe this is a bit confusing to write that as an integral of t, and maybe I should say that nu of omega is above t. That's better. And then this is 0. Right, which was the conclusion we were trying to reach. And it's interesting to note at this stage that we're really exploiting the fact that we've defined the Ito integral process to process as the unique continuous martingale that equal to the Ito integral process to variables for every t, for almost every t. So it's very important that we've chose continuity, because this allows us to run arguments like these ones and bootstrap from having information purely on the rational, where we can take countable unions of set of probability 0, to having a information on all the values of time. So continuity is critical on that. That allows us to restrict our attention to rational times. Okay, now that we have this, we can get rid of the L infinity assumption, and that is the next corollary. Right, so the corollary tells us that if you have two processes in H2, drop the L infinity extra assumption, and a stopping time, always with respect to the Brownian filtration, if the two processes are equal up to a stopping time, then the integrals are equal up to that stopping time. Okay, so we're going to apply the previous lemma. Now, obviously, we're applying it to f minus g, so f minus g is going to be 0 up to the stopping time, and then the integral of f minus g is going to be 0 up to the stopping time. Now the point is to drop the unfit assumption, and the way you do it is very simple. You just approximate f by f times the indicator function of the set where f is smaller than n, and you do the same with g. Now for every approximation, the previous theorem applies, and then by dominated convergence, f is the limit of fn and g is the limit of gn. And so Ito isometry tells you that the integrals converge to each other in L2, and then you take a converging subsequence, a subsequence that converge almost surely, and you get the equality almost surely. All right, so that's a simple argument to get rid of the L infinity assumption. Just truncate the function up to a level n, and that gives you an approximation that works in L2 norm, and therefore the property that you have for the integral of the approximation you keep for the integral of the limits, understood in an L2 sense.